Hi everyone, welcome back to the course on Introduction to Material Science and Engineering offered by EdupediaWorld. The previous lecture we started and saw the concept of ceramic crystal structures, the basics of it. We learned about the influence of radius ratio of the cation to anion on the type of geometry that we'll have. Today's lecture will see some specific examples of ceramic crystal systems and the geometry associated with them. So what are the things that we'll study in today's lecture? We'll study, generically speaking, one that is known as AX type of crystal system. What does AX means? This will stand for anion part and this will stand for cation part. So there is one cation and one anion in the ratio 1:1. And what are the specific cases we will see? We will see sodium chloride or rock salt type, cesium chloride type, and ZnS type or zinc blend structure. Next we will see AMXN type. What does this mean? This means that the ratio of cation to anion is not 1:1. The specific example that we'll focus on is calcium fluoride, CaF2. Then finally we'll see an example where we have more than one type of cation. So we have A type of cation, we have B type of cation, and we have X type of anion, right? An example of that would be barium BaTiO3, right? This is one of the compounds which fall under the perovskite structure. We'll see about that. What exactly is the perovskite structure? So this is broadly what we'll study in today's lecture. Let's start with sodium chloride type or rock salt type of structure. So the cation to anion ratio for sodium and chlorine, that is Na plus is to Cl minus, radius ratio lies between 0.414 and 0.732. And as we know, this range of radius ratio gives us a coordination number of 6. Okay, and coordination number of 6 and octahedral geometry, right? Now octahedral geometry, what did we know? In octahedral geometry we knew that cation will be surrounded by 6 anions and vice versa. So some of the elements which or some of the compounds which follow the NaCl type structure are NaCl, obviously, MgO, MnS, FeO. These are all are examples of compounds which have NaCl type of structure. Now I have given you an idea about the holistic idea about what is the cation to anion size ratio, what is the coordination number, but what exactly is the structure? So here we have an image of NaCl type of structure. What we see here is that since chloride ion is the largest sized ions and Na plus is the smaller sized cation, and the largest sized anion, the chloride ions for NaCl type of structure lies at the 8 corners of the cube, of the larger cube, and at the face centers. So 6 face center, 8 edge corners. Okay, and where does the Na plus ions go? The Na plus ions go at the edge centers, so all the edge center, as we can see, and the body center, right? So how can we say that this is coordination number 6? Let's take this one for example. This has 1, 2, 3, 4, 5 and 6 atoms surrounding it. So this has a coordination number 6. Similarly, we can say that it is in the octahedral void location. Why? Because again, these are the 4 planar atoms and 1 atom and 2 atom, one at top and other at bottom. Therefore, this has to be the octahedral void. Similarly, if you extrapolate this in the 3D, what you will see is this is not the property of only this cation. The same scenario can be seen for this cation, though over here it appears that it is at an edge, but if it were a 3D expansion, then this is same as this it's just a translated position. Okay, so this is my sodium chloride type of structure. Next, let's move to cesium chloride type of structure. Now cesium chloride type of structure, what we see is cesium and chlorine are quite close in size. They lie in the 0.732 to 1 range. Therefore, it will have cubic geometry. Sorry about this, it has to be coordination number 8 rather than 1. That's a typing mistake. So coordination number 8 because it is cubic, and as I said in the last lecture, this is not body centered cubic. This is cubic structure in which the 8 anions will be at the 8 corners and the cation will take place at the central void. It's not body centered cubic because the central body centered atom is not the same as the edge center corners. For a body centered cubic, the body center and the corner atoms should be same. So this is my cesium chloride type of structure in which chlorine lies at the corners, cesium lies at the center. But this can be extrapolated in the 3 dimensions, and what we can see is if a cesium is here, there will be a cesium here, there will be a cesium here, cesium here. So alternatively, the chlorine is also actually surrounded by 8 cesium atoms. So it's just a perspective of visualizing with respect to what you are saying what. Next up, let's discuss about ZnS type of structure, the last type of structure that we'll discuss, for which we have 1:1 ratio of cation is to anion. Now ZnS type structure will have tetrahedral kind of arrangement. Okay, now tetrahedral kind of arrangement, what does that mean? That means that we are in the 0.225 to 0.414 range, right? The radius ratio I mean, and the coordination number will be 4. So let us see the structure. What exactly is the structure? We have Zn2 plus and S2 minus. So what we'll have is the sulfur atoms. The sulfur atoms will go at the corners, 8 corners, and the 6 face centers. So effectively what we have is sulfur 1 effective from the corners and 3 effective from the 6 faces, which means 4 effective sulfur atoms in one unit cell. Now where are the zinc atoms located? The zinc atoms are located at the tetrahedral voids. Okay, but one thing to note here is that the zinc are not located at all the tetrahedral voids available. In this structure there are 8 tetrahedral voids available. Only 4 of them, the alternative ones, are occupied by zinc. How can I say the alternative ones? 1 is here, right? 2 is here, the diagonally opposite one. There another zinc might have been here also, right? This atom, this atom, this atom, and this atom forming, but it's not there. Or one might have been over here, but it's not there. So these 2 diagonal tetrahedral voids have 2 zincs, and these 2 diagonal tetrahedral voids have 2 zinc. You notice that in order to reduce the internal strain, what the structure is doing is it is trying to place the zinc at maximum distances from each other. So this zinc is here, this is diagonally opposite to there, that zinc. This zinc is here and diagonally opposite here, and this pair and this pair are itself diagonally opposite in the sense that they are perpendicular to each other. So this is my zinc blend or ZnS types of structure. So obviously Zn is also 4 in the 4 tetrahedral voids. Now other examples of ZnS type structure is ZnTe, SiC. These all fall under the ZnS type of structure. Now that we have seen the 1:1 ratio kind of structures, let us see examples of different ratio. The example which we'll see is calcium fluoride, Ca2 plus and 2F minus. So what we see is we have 1:2 ratio for cation is to anion. So we have more anions and less cations. Different charge on cation and anion, therefore different number of cations and anion. And for this specific case, that is CaF2, the size ratio is around 0.8, therefore the coordination number turns out to be 8. Okay, so it is a cubic kind of scenario. Now, in order to visualize how exactly is the CaF2 structure, what you need to do is think of this unit cell as composed of 8 different unit cells. How come? You need to draw a line over here, a complete plane over here dividing it, and a complete plane this way dividing it. So you have and one over here. So what you have is one whole cube, one cube over there, one cube over here. So the whole thing, basically what I mean is, if you have a cube, right, and if you draw 3 set of plane perpendicular to each other from the centers, okay, then what you will get is 1, 2, 3, 4, 5, 6, 7, 8 smaller subcubes. Okay, so think of it as 8 different smaller subcubes. Now what is happening is, in each subcube all the corners are occupied by fluorine. So here, 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 there, 2, 3 and 4, right? So this subcube has 8 fluorines, this subcube will have fluorines over here, here and here, and already those things. So this is exactly the arrangement you can see here, right? So all the subcube, all corners are filled by fluorine atoms. Now where does the calcium atoms go? The calcium atoms go at the alternative octahedral voids. What do I mean by alternative octahedral void? If you take the first subcube, then there is a calcium atom at the octahedral void of that subcube. Then we do not have calcium atom at subcube 3. If we have calcium atom in subcube 1, then the next subcube where we will have the calcium atom is subcube 5. The next calcium atom which we will have will be at 1, 5, then over here in this one, and over there in the 7th one. Okay, that's what we see here. One calcium atom is here, one calcium atom is here. These are diagonally opposite. One calcium atom here, one calcium atom here. These are diagonally opposite, and these are also in the diagonally opposite cubes, right? So this gives you idea about calcium fluoride type of structure. Now let us see a little more complicated structure in which we have more than one cation. Specifically in the example we will see BaTiO3, we have 2 cations, one is Ba and other is Ti. Now what are the charges? We can write this as Ba2 plus, Ti4 plus and O2 minus, but we have 3O, thereby balancing out the charge. This structure is known as perovskite structure. And how does the structure look like? The structure looks like the Ba, we have effectively one Ba atom. It goes at the 8 corners, that makes it 1. We have 3 oxygen atoms, that goes at the 6 face centers, which makes it effectively 3. And we have one Ti atom which goes at the octahedral void created by the oxygen atoms. Now this Ti4 plus ion is located at the center, the body center, but under stress, mechanical stress, what happens is that the Ti shifts either above or below, thereby there is a dipole kind of scenario created. The charge is not symmetrically at the center now, and this leads to interesting properties which provides very useful application for the perovskite kind of structure. We'll see this in future lectures. We'll revisit perovskite then, but for the time being, remember the structure: the barium Ba ions at the 8 corners, oxygen ions at the 6 faces, and Ti ion at the center. This sounds complicated already, right? Now one more type of structure is called as spinel compounds, and the spinel compound basically has the formulation as A, the first cation single, second cation has 2 atoms, and the anion has 4 atoms. So effectively we have 3 cations and 4 anions. That kind of structure is known as spinel compound, but we'll not go into the details of a spinel compound. We'll close our lecture at perovskite kind of structure. Hope the last 5 slides with 5 different type of structure gave you insight about the vast variety of crystal structure that can exist in a ceramic system. And with vast variety of structure comes vast variety of properties which can be used under different kind of application scenarios. Next class, what we will do is we'll start to learn about crystallographic directions and crystallographic planes. Till then, have a great day. Goodbye.